So I do intend to solve the quiz problems as examples 2 and 3. So we'll get there. But let me begin with a word of prayer. So, Dear Father, we thank you for this day. Again, I thank you for this class. I just ask you to be glorified in what we do, that we'd all understand a little bit more about how to work with eigenvectors and how to use them to solve differential equations. Lord, in your name I pray, Lord Jesus. Amen. All right, so let me just recap here. Last time I worked on this example, pretty much all of class, but we took like a large theoretical detour, right? So if you really look back at last class, we really only calculated stuff for about maybe 15 minutes. Most of the other time was devoted to talking about like what's a solution matrix and some other things, which we need to know about. And certainly I have more to say about those, but for the record, we are in chapter 9. Some of you asked me, like, where are we? We're in chapter 9 in the textbook. And I haven't covered like all of sections, like 9.1 through 9.4 or anything like that, but covered bits and pieces of it. The eigenvector stuff, I believe, is section 9.5. I don't think the magic equation is completely clear in the book, so there are things you'll see in class that won't be as clear in the book, all right? So, just saying. Now, and hopefully I'll get the projector out here once I'm done with these in-class examples, because there are like 10 pages of worked out examples in my notes that you should be aware of, all right? So, and I don't think I've used them for class yet either. So, all right. So first of all, we had that matrix. We solved remember we worked this out. We found eigenvalue 3 with algebraic multiplicity 2. We found lambda eigenvalue 7 with algebraic multiplicity 1. That means how many times it's repeated in the characteristic equation, all right? Now there's a theorem. There will always be at least one eigenvector for every root that you find in your characteristic equation. So like if I've got eigenvalue whatever, there is at least one eigenvector. You can be assured of that. There may be more, there may not. For this one, we did find the eigenvector with eigenvalue 7 to be this guy. And we did find that the eigenvector with eigenvalue 3 is that guy. But that was it, right? So as I introduced the idea, we need to seek something more to complete the solution. We need to look for what's called a generalized eigenvector. In this case, order 2 for eigenvalue 3. The way to find that is to solve the chain equation. So the chain equation, you take a minus 3i times the vector you're looking for, u3, equals to the eigenvector you already have, which is u2 in my current example. So that gives me this equation, right, which is a minus 3i times the vector I'm trying to find, uvw, all right, equal to 1, 0, 0, which is the eigenvector with eigenvalue 3 we already found. See, this goes here. So there is an ad hocness to this calculation, right? Like if I had chose, like we made a u equal, I think we chose u equal to 1 here, right? If instead of choosing u equal to 1, I chose u equal to 8, that would have put an 8 here. And that would have affected my u3. See, instead of having 2v equal to 1, I would have had 2v equals to 8. And that would have ended up giving me a u3 as, 0, 4, 0, right? So there is some ambiguity in terms of how we choose the eigenvector, but once you choose the eigenvector, there's a certain specificity which is forced on you by the chain equation. However, notice that as we look at these equations, we get 2v equal to 1, fine. The middle equation, though, tells us nothing, right? And then the fourth equation is just 4w, fourth equation. The third equation is 4w equal to 0, right? So if you look at these, we've got no what? No u equation. So that means, yeah.
Are the u's supposed to be switched? Because the 2 over there is 7, and then you have u1 as 7 over there. Shouldn't it be 3 for the first, and then 7 for the second?
Oh, yeah, I'm sorry. Sorry about that. Thank you.
So the 3 is supposed to be the second eigenvector?
Yeah, I made 3 the second one because I knew that this third vector was the more complicated one, which we may or may not have gotten to last class. Apparently not. Yeah. So, Sorry about that. Usually people, the usual like nomenclature, like the standard ordering for things, is you tend to see people make the eigenvalue that is the least, like the most negative one is the first one, and then they're just ordered from like in their ordering. So if I had eigenvalues 1, 2, 3, 1, 2, 3, a million, I would make 1 the first one, 2 the second one, 3 the first one, and like a million would be the fourth one. They usually put in order. So I violated that convention here, but it's not written in stone. Anyway, so there's my generalized eigenvector of order 2 right there. What do I do with it? Well, I use the magic formula, right? So you come over here. I talked to you guys about why this is true last time a bit. If we put lambda equals to 3 in here, we get this lovely formula. When I multiply that by the generalized eigenvector of order 2, I simply distribute it through the, so every one of these matrices in this infinite sum of matrices acts on the vector, but most of them are kind of boring, see, because by construction, a minus 3i times a minus 3i squared times u3 is what? It's a minus 3i, and then there's another a minus 3, but a minus 3i times u3 is u2. But then by construction, that is 0. See, because u2 was an eigenvector with eigenvalue 3. So what that means is this is 0, the cube is, everything here is 0, except for these first two terms. And the first two terms are simply u3 and tu2, both of which we've already calculated. So I put that, here's the details right here. And then the general solution, so this is a generalized eigenvector solution, you could call it, all right? This is not something we would have found in section 9.5's technology, all right? If you want to use the book. But I think I've given you a complete and coherent story in class, so like, Anyway, so, and then here is the general solution. C1 times the first eigensolution plus C2 times the second eigensolution plus C3 times this new fancy schmancy generalized eigensolution. So the moral of the story here is when an eigenvalue is repeated, we may or may not have enough eigenvectors to like work out the problem. If we don't have enough eigenvectors, then we have to go looking for generalized eigenvectors, which we find by solving the chain condition. All right. Now I didn't put that on you for the quiz, right? The quiz, I just asked you to find the eigenvectors for those two problems. So let's look at that. So example 2, which is actually your problem 2, right, is this. So what are my eigenvalues? So we do what? 3 minus lambda, 1, 0, 3 minus lambda. Of course, if you remember, one of the things I told you guys, which was what? If it's a triangular matrix, the what? The eigenvalues are what? On the diagonal. So no surprise here that lambda 1 is equal to 3 and, twice. It has algebraic multiplicity 2. So there you go. Our eigenvalue is 3. And then we just have to solve a minus 3i times u1 equal to 0. But that tells me in this problem that 0, 1, 0, 0 times uv is equal to 0, 0. Which gives me what? That gives me the top row, gives me v equals 0, u is free, right? So we might as well make u1 equal to what? I'm going to make u equal to, the one thing I can't do, there's one choice, there's one tree from which you may not eat here, right? Yeah, 0, 0. Right? 0 is not an eigenvector. It's the only one you can't have. So 1, 0, I like that. That's a good choice. So there you go. That's my eigenvector. What's my eigensolution? That tells me x1 equal to e to the 3t times 1, 0. I keep doing x1, but I meant to say r. Well, notation. I'm going to do r because I've used x and y as scalar variables here. But this right here, you could call it r1. This solves, right? Solves star. If I call this thing star. And so that would be a complete solution for problem 2. Yeah.
Do you not need a c in there at all?
No. Well, I said just find a eigenvector solution. So you could multiply that by anything. You could multiply that by like 32, 42, pi, e, whatever. And that's reflected in that ad hoc choice we made for you. It's the same choice, yeah.
So the other day I was looking at one of the old quizzes, and it was essentially this, but just with, like, instead of 3 is 4.
Uh-huh.
And so you get 4 twice, and then after you got u of 1, you like did u of 2, and then you like flipped it, so you had 0, 1.
Oh yeah, I'm not done yet.
Oh.
I mean, this is not the whole solution. The whole solution theoretically has to be a linear combination of 2 linearly independent solutions, right? So this is a solution, but it's not the general solution. I know it sounds like I'm lawyering you. In some sense I am, but you know, what I'm trying to say is, like, I didn't require of you the full story, right? Like,
This is just like, this still passes as a solution.
yeah, like, just because the problem, I didn't say find the general solution. I just said find an eigenvector solution. I hope I said that. Okay, good. I mean, I messed up the vec on the first problem. So let's finish it then. So to finish it, we do the same thing that I just did over here, which is to solve the chain condition. So the chain equation here, we're looking for a minus 3i times u2 equals to u1. This is easier than my example 1 from last class because it's a 2 by 2 problem, right? But even for the 2 by 2 problem, you don't always have enough eigenvectors. But I can give you guys like a bird's eye view of when this can happen in the 2 by 2 case. I think it's far. Well, I shouldn't say it for sure, but I tell you this much. I know that if it's either upper or lower triangular, this happens. I'm not sure if anything past that happens right off the top of my head, but I probably should know, for shame. Don't tell the other instructors, I don't know. All right, so we got 0, 1, 0, 0. It's that matrix again. uv equal to u1, which we chose to be 1, 0, right? Now I'm trying to find u2, right? This is my u2. This is the u1 we already know. So what's this give us? We get v equal to 1. U, free. So I would suggest that we make u2 equal to 0, 1, which I think is like what you're saying is found in the quiz, right? Great. And then to finish this thing, I use the, the magic equation. So I do e to the ta times u2 is equal to, e to the 3t times I plus t times a minus 3i plus dot 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 dot, right? u2 rather. And that gives me e to the 3t times u2 plus tu1, which in this case is e to the 3t times my u2 was 0, 1 plus t times 1, 0. So therefore, my general solution has the form c1 e to the 3t times 1, 0 plus c2 e to the 3t times, you can add that stuff together, right, in the brackets over there. Like, add this together, what do I get? I get a t in the top component, and I get a 1 in the bottom component. So there you go. That, my friends, is the general solution to this system. If you want me to go back to scalar notation, what this means, right, is that our solution is x is equal to like c1 e to the 3t plus c2 t e to the 3t. And our y is just c2 e to the 3t. So some people some differential equations instructors are like insistent you write the answer that way. You know, I'm not that person. I personally am very happy if you write your solution in vector format, illustrating that you know what's going on, you know. This is the same answer, what's boxed in red and what's boxed in blue. So short of me putting, you know, some specific demand on the format of the solution, you can leave it either way. But if you leave it as a scalar, when I didn't ask for it, I'll probably be annoyed. But I'm not going to take your points. I'll just be annoyed because you worked harder than you needed to. You know, I do like you guys to be lazy. Believe it or not. But be lazy in a smart way, you know. Okay, so what's next? Well, we got this problem 1 on your quiz, right? Now, I told you the eigenvalues were 1, 7, and 3, right? So what we have to do is we have to solve a minus I times u1 equals to 0, right? But that is 2 minus 2, 8, 0, 4, minus 2, 0, minus 4, 2 times this vector equal to 0. Right, we have to solve that system. And let's see here. A minus 7i u3, we'd have to solve what? Equal to 0. So you'd have to solve minus 4, minus 2, 8, 0, 1, minus 2, 0, minus 4, minus 1. UVW equal to 0. Solve that system, right? And then the third one, I'd have to solve this. And let's see here, 0, minus 2, 8, 0, 2, minus 2, 0, minus 4, 0. Right? So I got this problem out of the book because I knew it had nice eigenvectors, and my hope was that it would be easy enough to work out in class. But I do wonder how many of you were able to solve these. Yeah. Mm-hmm.
For the middle one,
Did I do something wrong?
middle is a 7. Shouldn't it be the middle of the whole one? Should that be -2?
It should. Thank you.
And then the
Excellent.
bottom right, should that be -4 also?
3 minus 7 minus 4. Thank you. Anything else I do? So did everybody at least set this up? Did you try to solve these? Then you got stuck because your linear algebra is not quite developed, maybe, right? So the way to solve these carefully and methodically is with row reduction, right? Like that's the best way to do it. So I probably can do one of these in the time we have. I'll pick the last one here. So this one, what does this tell me? Let me just pick on this one. See, this one's easiest to solve because what's the condition on U?
It's free.
It's free, right? So by logic, V and W must be 0 here. Sorry. Oh, rats. I know that because of linear algebra. Well. For those of you who've had 221, these columns are obviously not multiples of one another, right? Which means that these are linearly independent, which means that the nullity of this matrix is 1. So I know there's just one solution. And I know that making u1 equals to 1 and v and w equal to 0 work. Actually, this is a method, by the way, guys, that works. Whether how much linear algebra you know or not, this is a method we can use here. Notice that u3, you may like, you can guess? Well, yeah, guessing is a method.
Couldn't you have v?
Yeah.
Oh, I'm sorry. I meant to put, oh, so I'm wrong?
Yeah.
Woohoo! So this doesn't work.
No, it does. You can plug them in and see that v equals 0.
But if I put v equals to w, I'm in trouble down here. See, if I tried like 1, 1, 1 as a solution here, when I multiply 1, 1, 1 by this one, I get back a -4 there. So like that's not going to work. I have to have v and w both 0.
But you can solve it with algebra.
Oh yeah, yeah, you definitely can do that. Oh, no doubt. I'm not saying you can't. So this is 4v, minus 4v equal to 0. So therefore v equals to 0. Once you know that, it's easy to see from 2u, rather 2v minus 2w. If I was just solving instead of talking, we could probably have solved these by now. W equals to v equals to 0, right? So there you go. That is the algebra which supports my guess. It wasn't hard. The third one's not hard. I think the first two, well, let's see here. These are the same equation, right? So since these two are the same equation, I can just focus on the first two and basically just work on substituting one of those into the other. So like, let's see here. So the second equation would tell me that 2v minus w equals to 0 if I divide by 2. And then the top equation is 2u minus 2v plus what? 8w equal to 0. So if I plug this gives me what? This gives me v. Well, w equals to what? 2v. So if I plug that up into here, I get 2u minus 2v plus 8 times 2v equal to 0, right? Which then gives me that 2u 10 minus 2 is 8 plus 8v equals to 0, which gives me that v apparently is equal to minus 2u over 8? 14? What did I do?
8 times 2.
Oh, 8 times 2 is 16, isn't it? Yeah. Duh. Me, not you. 14. All right. So 14 apparently. So minus u over 7. So there is a pretty obvious choice here. We should let u equals to 7. Because who wants to have fractions, right? And so my vector for, what was I working on? u1, apparently, I can have 7. And then my v was what? 7 over minus 7, which is minus 1. And my w is 2v, which is minus 2. So I do actually think you guys can solve these. If you know linear algebra, there is a clear, systematic way of doing it. If you don't, you just have to kind of attack them and combine them and work on eliminating. And if you know a little bit of theory, it can guide you. There is at least one solution, and it cannot be the 0 solution. There have to be infinitely many of them, actually. So when I say one solution, I mean there's a whole family of solutions always. All right. So the eigenvector for eigenvalue 3 was actually 1, 0, 0. And so yeah, like I found minus 7, 1, 2 for eigenvalue 1, 1, 0, 0 for eigenvalue 3, and 5 minus 2 minus 5 minus 2, 2 for 7. Wait a minute. Oh, I'm sorry. I was looking at the website. It has numbered the eigenvalues not the same way as on my board, so I've got to take my answers and move them around. Anyway, more next time. Have a good weekend, guys.